Should I keep going?
Yeah, you can continue.
Thank you.
Okay, so this is work that I did at Michigan State while I was a graduate student. This is my thesis work, but so I just want to present some results because the paper is essentially ready and will be distributed as a Christmas present for the collaborators. So the first thing is that the X-ray sky is alight with activity. So of course we can't see it with our bare eyes, but if you put a useful X-ray telescope in the sky, I unfortunately don't think I can play this because I'm using my very fancy Lawrence Livermore laptop that can't do anything. But if I were to be able to play the video on the left, you would see that as there are a lot of X-ray sources in the sky from various astrophysical sources. And on the right, since we have Superman with his X-ray vision, if he looked up at a binary neutron star system with a main sequence companion star, he would be able to see that as material is accreted onto the neutron star, eventually might ignite in thermonuclear runaway, and you have an X-ray burst that we can observe with, for example, the Chandra X-ray telescope. And so there's a lot of stuff going on in terms of the X-rays, and the reason why, as nuclear physicists, we are interested in this is that, how do I progress the screen? Ah, there we go. Okay, we need nuclear physics to understand accreting neutron stars. So here is another look at what an accreting neutron star system looks like. So you have your companion star, your massive companion star on the radially massive, I should say, companion star on the left, and it accretes onto a neutron star. Eventually, it ignites. And you can see here in this graph on the bottom left, very famous figure showing X-ray bursts, which are these sharp spikes that you can see on top of an constant X-ray flux. So these are what we call X-ray bursts. But we also need the nuclear physics to understand what's going on once accretion has stopped. So when the neutron star has entered its quiescent phase, so when the accretion tap, so to speak, turns off, and there's no more bursting, the thermal evolution of the cooling neutron star crust depends on nuclear processes that continue to occur in the outer crust of the neutron star. So if we observe what a neutron star, a cooling neutron star, does after it enters its quiescent phase, it actually tells us a lot about what the internal structure of the neutron star is. And one thing that is extremely exciting about this is that we can learn about the interior structure on the time scale of perhaps a decade. So if you look at the plot on the left, this is showing a log scale on the x-axis, a log scale in days. The years are marked out where the observations are. And you can see that once it's entered its quiescent phase, you have this cooling behavior that represents what's going on in the outer crust. And this outer crust essentially is very similar to what we consider to be a solid lattice, essentially. So you have a cooling crystal of electron gas. So if you look at the corresponding layer on the figure on the right, and as it continues to cool, we can observe further into the interior of the neutron star. So in a period of about 2 years, we're looking at the superfluid neutrons. And then wait a few more years and you're observing the nuclear pasta that's essentially at the crust core boundary, and everything inside tells us presumably about the structure of the neutron star core. And so it's important for us to be able to extract the inner workings of the neutron star based on on these astronomical observations. But to do that, we have to know what additional nuclear processes are going on inside the outer crust. So these processes will transform ashes of X-ray burst as they are pushed deeper. So if you look at the, can you guys see my cursor, by the way?
Yes, we do.
Okay, thank you. So if you look at the stratified plot on the left here, as you go deeper, the Fermi energy of the neutron of the electrons in the crust is increasing, and so when you cross the threshold for electron capture, so when the Fermi energy is equal to the electron capture Q value for one nucleus to another, you essentially convert the nucleus into the more neutron-rich species. So you can imagine that as you are going deeper, you will end up transforming into increasingly neutron-rich species, as shown in this animation. So you go from a Z n nucleus to Z minus 2 n plus 2, as shown here. So, and the plot that I showed before, the cartoon I showed before was for zero temperature crust. Now we know that this is not likely to be the case. And so instead of having sharp boundaries as shown before, you actually have this coexistence. So you have one zone, so to speak, of a nucleus and another zone that's kind of stratified. But there's a layer in between where these two species can coexist. And the reason for that is because you have not a sharp boundary for the electron Fermi energy, but sort of a tail as to be expected when temperature is not zero. And in this coexistence region, you can have Urca cycles of consecutive electron captures and beta decays. And these two processes lead to strong neutrino emission from the crust. So you can imagine, for example, we have a nucleus that's living as a Z-1 species. It beta decays through the ground state, and I'll explain why this is important in a minute. It beta decays through ground state and emits a neutrino that just flies off. And then because the Fermi energy of the electrons is high enough, it actually electron captures back into the ground state of this AZ-1 nucleus, and then the cycle repeats many, many times, and you just have a slew of neutrinos that are just leaving the neutron star crust, taking energy away, leading to cooling. So for an Urca pair, or Urca chain, I guess, also to be important requires two important things. One is that there's a large abundance of that mass nuclei in the ashes. So if, for example, A equals 61 nuclei did not exist in X-ray burst ashes, then it doesn't matter what the nuclear properties are, it just would not cool, right? The second thing, which I mentioned before, is this strong ground state to ground state beta decay transition. And the reason for that is because of even though the temperature is not zero, it's not some absurd number either. And that means that you can only have phase space for the electrons around the Fermi energy, which means that you cannot beta decay to excited states unless they are extremely low-lying. And we're talking about, like 40 keV low-lying. So for the most part, we don't really see that. So just for a simplistic picture, we tend to talk about ground state to ground state beta decay transitions. So the question here is whether vanadium-61 is a significant Urca cooler. So A equals 61 is a really good candidate. So the mass 61 chain is a good candidate for strong Urca cooling for two reasons. One is that, again, the mass 61 ash is abundant. So if you look at the plot on the right, these are the odd A masses, odd A abundances for a typical X-ray burster. And you can see that mass 61 ash is very abundant. It's the second most abundant odd A mass. Is there a question? Sorry. Okay. Sorry. Anyway, so the second reason is that if you look along the A equals 61 mass chain, starting with cobalt 60, A lot of these ground state spins are close to each other, which means that it's likely that there is an allowed transition between the ground states of these nuclei. So from electron captures and beta decays in the opposite directions. And so if your beta decay is allowed, it's likely to be faster. And so the measured beta decay, ground state to ground state beta decay strengths have been done for chromium to manganese to iron to cobalt. This is the loss transition here that hasn't been experimentally measured, and that's essentially that was the goal of the experiment that we did at the NSCL. I should mention that the QRPA prediction for this transition is extremely strong. So it is 4.35, which it doesn't, I guess, mean anything by itself, but it's a very strong transition, and I will show later a plot that demonstrates how much stronger it is compared to the other transitions in the same mass chain. So just a bit about the experiment. So this was done at the NSCL, a vanadium-61 cocktail beam, so there are some other contaminants, was produced using a selenium-82 primary beam at the coupled cyclotron facility. It was impinged on a beryllium target and then purified through the A1900 fragment separator and transported down to the S2 vault, which is where a lot of decay studies are performed. And so we had a beam of about 80 particles per second that was mainly these 4 species of vanadium-61, chromium-62, manganese-64, and iron-65. But as you can see with momentum corrections from the I2 scintillator, these are actually fairly well separated, and we can study individual species very cleanly. So to measure the ground state to ground state transition strength of vanadium-61 beta decay to chromium-61 is not straightforward. Essentially, the technique is that you measure all characteristic radiation, and then you take 100% minus the beta decay to every other state that you can see. So if you look at the simple schematic, when you beta decay to an excited state, for example, one that's below the neutron separation energy but is an excited state, it decays by emitting a gamma ray, which you can see. And so you can identify the entry state, for example. If it decays to a state that lies above the neutron separation energy, you can also decay by emitting a neutron to produce, in this case, chromium-60. So in the other scenario, when you decay straight to the ground state, you don't see any gamma rays, you don't see any neutrinos. You see the electron, but because you also produce a neutrino, you cannot tag specifically on the electron because you see a beta decay spectrum rather than a beta decay electron with a single energy. And so the idea here is that we would use the summing sodium iodide detector, or SUN, to measure the gamma ray cascades that come from excited states, and we use NERO, the neutron emission ratio observer, to measure the neutrons that come out. So if you combine all of those results and you take 100% minus the population of the excited states, you would see, or you would be left with the ground state to ground state transition. So here is the schematic of the experiment. So the beam is coming in this case, from the left. In the first part of the experiment, SUN was not being used, so it was just housing an empty beam pipe. And the beam would be implanted in a silicon double-sided strip detector that's sitting at the target position of NERO. So a beam of vanadium-61 beam particle would implant on the silicon DSSD. It would decay, and if it produced a neutron, the neutron would be emitted. Well, the neutron would be emitted. It would moderate in NERO, and eventually be detected either by a helium-3 tube or a boron trifluoride tube that is sitting in the NERO matrix. And so as with proportional counter systems, you essentially count how many neutrons you see And then out of the total number of beta decay events that you observe based on coincidence between the beta decay electron and the implant, you can say, okay, this is how many times you have a new beta delayed neutron emission, and so you find your PN value. So here is the result. If you look at the neutron-gated vanadium-61 decay curve, which is this one here, it's very well fit to the decay of vanadium-61 with the half-life. If you compare the inset, the neutron-gated decay curve is in red and the ungated decay curve is in blue. And essentially, the ratio of those two, which is not quite true, but close enough, is your PN value, which is in this case about 14.5%. And so it is actually really important to measure this because A, 14.5% is not a trivially small value. And B, while it is possible to use sun to detect neutrons, it's much better in our case to have a separate and independent confirmation of what the PN value is. So the second part of the experiment, we used sun to measure the gamma cascades. So the beta counting station here has been removed, and instead a mini DSSD, a silicon mini DSSD has been inserted at the target position of sun. So now the incoming beam particles are implanted in the DSSD at the target of sun, and when it decays, all the beta delayed gamma radiation is measured with sun. And so the nice thing about sun is that because it has such an amazingly high efficiency, it has an advantage that you don't necessarily care so much about individual gamma rays in each cascade. You just look at the sum energy, so it detects all of the gamma rays. And if you look at the peaks in the total absorption spectrum, you essentially reproduce the level scheme of the nucleus. So this here is the ungated total absorption spectrum, and you can see that there are peaks that are the levels, the excited states in chromium 61, which is the daughter nucleus, manganese 61, which is the granddaughter nucleus, and of course the beta delayed neutron daughter, chromium 60 as well. So that's one of the very nice things about using a detector, a TAS detector like sun. So now that we have the TAS spectrum, the idea is that you need to reverse engineer the TAS spectrum to get the beta feedings. So for the levels that are known, we can simply do JINA simulations based on the gamma branchings. So for these levels under 2.26 MeV, these are previously known levels reported also by an NSCL group, Scott's Heda, in 2014. And above that, we use this software, this statistical software called Dicebox, to essentially model what the quasi-continuum looks like. And so what we do is that instead of saying, okay, there's a state at X MeV, Y MeV, Z MeV, we say at every bin of energy, there are these gamma rays that are expected to come out. And so we take the results from the Dicebox simulations and we use that as an input to JINA-4 and essentially produce what I call templates. So essentially produce what the radiation from that state or that bin of states is expected to look like in sun. And so these templates for each state or each bin of states will build up your total absorption spectrum. So essentially the total absorption spectrum is a linear combination of these templates. So you can take that and you fit to reproduce your total absorption spectrum. It is not shown here, but at the same time, we are simultaneously fitting the singles spectrum as well. And so there were a total of 82 templates that we made from JINA-4, and we fit them using variety of methods, but to independently confirm that the fit was correct and not stuck in a local minimum. And we reproduce the total absorption and the single spectrum. And using that, we can recover the beta feeding intensities. And the important thing about using sun and its advantage over, say, a germanium array is that you can overcome this Pandemonium effect. And so the Pandemonium effect is extremely well known. It's been known for years. But the idea can be simplified to say that if you have two states, two excited states in your nucleus, you can determine the beta feeding of the lower lying excited state by taking the number of times you see it decay, the number of times you see it decaying, and subtract the number of times it is being fed by the state above it. And that gives you the feeding of the lower lying excited state. The problem with this is that if you have extremely high density of states, if you have a lot of transitions, if you have some very weak transitions, compounded with the lower intrinsic efficiency of a germanium array, you will individually miss gamma rays. And that leads to a systematic overestimation, essentially, of the population of the low-lying states, because you've missed the transitions from the higher-lying states that you would normally subtract off. And so you can see, essentially, you can see that effect here when you compare the lowest lying state feedings determined in this work. So here we have about 2% to 2.5% for some of the lowest lying states. In 2014, which used the Sega array, you can see that it's much higher. And that will lead to abnormally strong beta decay transition strengths for those lower lying states. So that is extremely obvious here for the ground state transition strength, where Scott estimated an upper limit of 40%, and in reality we see that it is much lower, about 7.5%. So what this means is that if you use a germanium array, there is a high likelihood that the reported beta decay feeding strength for the ground state is going to be overestimated. So you make that transition strength significantly stronger than it really in reality actually is. So now that we know and we have measured the beta decay transition strength for between the ground states of vanadium-61 and chromium-61, we can use that to study what the Urca cooling strength of the mass-61 chain is. So on this plot here, on the top panel is the abundance of each nucleus in the mass-61 chain. So it's normalized to the total mass-61 abundance. And on the bottom panel, you have the cooling strength as a function of column depth. So as you go to the right, it becomes the Fermi energy, the electron Fermi energy increases as you're going deeper. So you're going to increasingly neutron-rich species on the right, onto this axis. So I will explain the animation as it's being played. So as you're going deeper, once it hits the Q value for transitions, you essentially morph between species of the mass-61 chain. So you go from iron to manganese to chromium to vanadium and titanium eventually. And so if you look at the different lines here, so the QRPA prediction that I mentioned was extremely strong, 4.35. It gives you, whoa, where did my cursor go? Okay, it gives you a very strong cooling effect. The previous limit from Scott's work in 2014, the 40%, still gives you an extremely strong effect. What we have measured is this blue line here in the center, and the green band is our error bar, gives something that's significantly more modest. However, I will point out that since this work has been completed for the mass equals 61 chain, the Urca cooling strength of the entire chain is now experimentally constrained. So in a comparison to other mass chains, so the red box here, so this is abundance multiplied by luminosity, so it's the cooling strength. If you look over here, this is the mass 61 chain. This is the QRPA prediction up here. So that would make it far and away easily the strongest Urca cooling chain. This is this red error bar is what we've measured, which brings it down to a much more modest level, but nevertheless still fairly significant. And I should mention that because this is convolved with the abundance patterns, depending on reaction rates of nuclei in the RP involved in the RP process, it is possible that this number goes up if mass 61 nuclei are even more abundant than we think they are. So in the future, one of the big things that's come up is not only about Urca cooling in X-ray burst ashes, but also Urca cooling in superbursting systems as well. So Zach Meisel and Alex Deibel have found that in superburst ashes, calcium-55 is far and away the strongest cooler. I mean, as you can see here, this is a log scale, so this is orders of magnitude larger than its nearest competitors. And part of the reason for that is the narrower superburst ash distribution, but also because it's much more abundant. A equals 55 is more abundant in superburst ashes. And the reason why this is particularly interesting is that an effect of an Urca cooling layer forming is that it thermally decouples the layers below it and above it. And so if you have any deep crustal heating that goes on below, deeper in the neutron star than where your Urca layer exists, it cannot transport that heat. The heat does not pass the Urca cooling layer up to the ocean, which is where the carbon emission layer that powers the superburst is. And so this places significantly more importance on the strength of the shallow heat source, the currently unknown shallow heat source. And so understanding Urca cooling in superbursting systems is extremely important for this reason. And so this experiment has been approved. It's going to run at NSCL at the end of March. So results are hopefully going to come soon. So just to reiterate some of the conclusions, so the vanadium 61 ground state to ground state transition is weaker than theoretically predicted. However, it is still fairly strong amongst its Urca cooling brethren, I should say. And the A equals 61 mass chain is now completely experimentally based. So the Urca cooling strength for that chain is no longer contingent on any sort of theoretical predictions for the nuclear physics strengths. On top of that, this combination of using total absorption spectroscopy and neutron counting system is able to determine reliable ground state to ground state transitions that are not plagued, I should say, by the Pandemonium Effect. So it makes them significantly more reliable. We've implemented this at radioactive facility at the NSCL, and that makes many, many more important Urca pairs within experimental reach. So more work needs to be done, and it can be done. Important transitions have been identified by several groups for future study, and so those are the things that we should be targeting in the future. And so lastly, I just would like to thank all the people who've been involved in this work, both from the experimental point of view, but also from the theoretical computational point of view. Thank you guys for participating in this seminar. I understand that it's right before Christmas and probably everyone wants to be eating food right now. And so thank you everyone, and Merry Christmas.
Thank you. Please, if you have a question, you can turn on your mic and ask your question.
So what is the reason for big discrepancy with the results of 2014?
So they did not consider, if I go back. Okay, actually here you can see it. So basically the huge difference comes from the quasi-continuum. So the 40% upper limit was determined by taking the transitions observed to the excited states that they did see. But the highest excited state that they did see was 2.26 MeV. The Q value for this beta decay is 12 MeV. So there's about 10 MeV of unexplored territory, so to speak, that didn't, that essentially did not get subtracted away.
Any more questions?
Yeah, can I ask a question?
Mhm.
Yep.
Hey, wait, it's Zach. I haven't looked. Are all of the interesting, or the ones that we think might be interesting Urca coolers, are those going to be accessible at FRIB, or will there be any that we still can't reach? Or have you had a chance to look at it?
So okay, assuming you have like 2 weeks of beam time, right? Okay, so not unlimited beam time. Almost everything is accessible now. The issue is that once you get too neutron-rich, you actually end up in a scenario where you're going so far deep into the crust that you have neutrons hanging out. And so neutron transitions occur and you basically kind of lose that Urca cooling effect. So right now we're already sort of on the edge of being able to measure all of the most important Urca pairs that you and Hendrik and others have identified.
Cool, thanks.
Well, if there are no more questions, we will have our next meeting on January 18th. We don't know the topic yet, but we will let you guys know. And I wish you guys a happy 2019 and see you in 2019.
Thanks, everyone.